So last time we talked about the sampling theorem, right? So sampling theorem is something that hopefully is familiar from signals and systems, although I think that we covered it in a slightly different way, when I did it this time. So now we kind of understand the relationship between what would be the Fourier transform of a continuous time signal and what would be the Fourier transform of a signal that is sampled. How can that go wrong? How can aliasing occur if I don't sample fast enough, and so on. And so what I want to talk about today are kind of two topics. One is kind of just filling in a little bit. At the very end of last lecture, I kind of breezed through this discussion of, if I wanted to design a certain continuous time filter, how would I design an equivalent filter in discrete time, right? So I want to talk about that just a little bit again here. And then I want to talk about the questions of how do you do changing of the sampling rate, right? So suppose that I, sample the signal at some rate, and now after the fact, I want to change the sampling rate to something else. So this kind of rate conversion happens a lot in real-world systems, right? Where one system is expecting data at 10 kilohertz, and the other system is expecting data at 12 kilohertz, and the question is, how do I make them talk to each other, right? And so that's kind of the topic of today. Okay, so last time kind of what we talked about was we had a continuous time signal. We multiplied that by, I think I called it D of t, which is basically this set of delta functions that occurs every t units to get some sort of a continuous time sampled signal. So basically what I'm doing is I'm taking the original signal, I'm multiplying it by this, and then I get, basically sampled impulses. And then, we kind of talked about how in practice what I would do would be I would convert this impulse train into discrete time. And that would produce my kind of discrete time signal, which is really under the hood, taking the every tth sample of the continuous time signal. And we showed that the Fourier transform of this kind of impulse train sampled signal was equal to this formula. Where what this formula means is that I get a bunch of copies of the continuous time signal, and those copies are centered at multiples of the sampling frequency, and they're 1 over t high as things used to be. And so to make that a little bit more understandable graphically, let me just draw a sketch. So what this means is that if this was my original signal, again, this here is the continuous time Fourier transform. When I look at this sampled signal, what I get is a bunch of copies, and if this was 1 high before, this now becomes 1 over t high, and the copies are centered at multiples of the sampling frequency. And kind of the upshot of last time was that, as long as I sample fast enough, then the copies don't overlap, right? If the copies do overlap, that means I have aliasing, right? So it was kind of hopefully easy to understand where aliasing comes from in the frequency domains. When I don't sample fast enough, this omega s is too close to the middle copy and things start to bleed in the middle, right? Okay, and so if we are interested in the DTFT, right? So kind of what we really care about is how is the DTFT of this discrete time signal related to these signals here? And all that really is happening is that I am taking so again, this is a continuous time Fourier transform of, so this is the original, this guy. This is the CTFT of this guy. And then the DTFT of x of n. So basically, I know that the DTFT has to be 2 pi periodic. And so fundamentally, all that I'm doing is I'm taking this guy and I'm squishing it down. I'm scaling the axis so that the copies reoccur at multiples of 2 pi instead of multiples of the sampling frequency, right? And so if this here used to be, so if this was the band limit omega b, and this was the band limit omega b here, what does this become? Well, so what I'm doing is I'm multiplying, what do I get here? So what I'm doing is I need to multiply this by 2 pi over omega s, right? Because what used to be omega s becomes 2 pi, what used to be omega b becomes multiplied by this ratio. And this is actually, 2 pi over omega s is just t, which was my sampling period from before. Okay. And so that's kind of what we talked about last time. And so let me just kind of be clear about, what we do in practice, right? So a lot of times, what I want to do under the hood is process some continuous time signals, but all I have are discrete time systems, right? So what I have here is discrete time processing of continuous time signals. So kind of the underlying model for what I want to do is I have some continuous time signal that comes in. I do some sort of a continuous to discrete or A to D converter where I sample that signal by some sampling rate. Now I get some sort of a discrete time signal. Now I can process this with some sort of a discrete time system to get some discrete output. Then I turn this back into a continuous time signal with a D to A converter. Again, I have to know what the sampling rate is here. And then what my output is some, output signal, right? And so now we kind of have all the pieces in place to understand how should I design this discrete time system to emulate an entire continuous time system, right? So if I wanted to have the effective frequency response in the continuous time world of this whole thing be some certain frequency response, how would I do it? Okay, so let me just label these systems. So we kind of understand now how all these pieces work, right? So piece number 1 was what I said earlier. So I know that the DTFT, right, so this is the DTFT because this is a discrete time signal, is equal to, I've got these copies of the scaled frequency response of the continuous time signal, right? So this is basically saying where the copies occur. They occur every 2 pi places. Then I know, how do I reconstruct the signal? Well, the reconstruction filter, if I want to go from D to A, is a combination between the original values and a whole bunch of sinc functions, right? So we talked about this last time because the ideal filter, right, the thing that takes me from let me just write this here. The thing that takes me from the spectrum of this back to the spectrum of this is just a low-pass filter, right? Because we showed that what I want to do in the frequency domain is notch out the middle copy, right? Once I've notched out the middle copy, I can think of that as something I can take the inverse continuous time Fourier transform of, where this guy here is just a low-pass filter. And I have to have this low-pass filter be of height t in order to compensate for the fact that the copies are of height 1 over t, right? And so this is all kind of just review from last time. Okay. And then in the middle, I know that I have some sort of discrete time system. So, 2 is just saying that I have some DTFT kind of relationship here, where this is the frequency response of the discrete time system. Okay. And so now I can kind of put all these things together to figure out what is the effective continuous time frequency response that I would get, right? So let's work backwards, right? So what I know is that my CTFT output is the reconstruction filter. So this is just a, reconstruction filter, which is a pulse, multiplied by whatever my discrete time output is, and I'm going to fill in what I know about this. So I'm just kind of working backwards about all the things that I know. Here is the spectrum of the original input. Okay. And so now I'm going to step back and think about, okay, so the continuous time, the continuous time filter is basically a combination of the low-pass reconstruction filter, whatever the original discrete time system was doing, and these copies of the frequency response, right? And so now what I'm going to do is I'm going to put the assumption on it. It says if this continuous time guy is equal to 0 for omega outside of this region, right? So this is basically like the band limit. So then what's going to happen is that effectively my output frequency response is going to be equal to whatever this discrete time filter was doing inside the band limit. And it's going to be equal to 0 outside. Right? That's exactly the effect of this reconstruction filter. That's just notching out the low-pass part, taking the middle copy. And so basically the effective frequency response that I have, so the overall effective frequency response, so what's happening is I have, in continuous time, some effective filter applied to my original continuous time input. These are all CTFTs. And my effective continuous time filter is just given by the discrete time filter scaled by a factor of t. Okay. And again, this is like maybe needlessly confusing, right? Let me just draw a picture to make it clear, right? So what I'm kind of getting at is that, this is what I ultimately get. This is the discrete time digital filter that I'm allowed to design. And I want to know, how should I design this to be able to obtain a given effective filter? And I know that I can't make a filter that does anything outside this region, because anything outside that region is going to get cut off by the reconstruction filter anyway, right? So I can really only design filters that do something to the middle, minus pi over t to pi over t of the signals. And if I wanted to make that interval wider, then I would need to change my sampling rate, right? And so, again, here's the picture. So the idea is that, I think this is actually a picture that I drew last time, right? So consider, h of omega as a digital low-pass filter, right? That means that it is periodic in the frequency domain. The copies reoccur at multiples of 2 pi. And I have some sort of a cutoff frequency, omega c. And again, this is my h of omega, what my previous page tells me is that my effective frequency response in the continuous time world is simply the middle copy of this scaled. Right? And so this kind of tells me that, if I want to get a cutoff of this time in the continuous world, I should design a low-pass filter in the discrete world that has this cutoff that is basically what I want multiplied by t. Okay. And so let me kind of totally drag this out with a worked example. Okay. So just to make sure everyone's on the same page. Okay. So here's my original signal. Xc of omega, right? And let's suppose this guy has some band limit. Okay, so that's my original continuous time Fourier transform. Now I'm going to do the the A to D conversion. I'm going to sample that guy. When I sample that guy, I'm going to get a whole bunch of copies. The copies are going to be centered at multiples of the sampling frequency, and they're going to be of height 1 over t. And this is the CTFT of my sampled signal. Now when I convert those impulses into the stem plot of the discrete time samples, I am scaling the x-axis so that the sampling frequency becomes 2 pi, right? That means now I have this guy. This is the DTFT of my discrete time samples. Okay. Now I design some sort of a digital filter. Okay, so now I can say, okay, suppose that I make for you a digital filter in the discrete time world that is kind of like a low-pass filter. So I'm going to notch out some frequency content. And let's suppose that the bandwidth of that filter is omega c. This is my filter that I want. Okay, so now when I filter that discrete time signal, I am going to cut out the middle part of each of these copies. So my next picture is going to look like this. So now I'm going to kind of have just the middle bit. This is going to be the DTFT of my discrete time filtered signal. Now, when I convert things back, right, so now I'm going to take this discrete time signal, I'm going to turn it back into this, for going from the stem plot to the impulses, right? When I go from the stem plot to the impulses, it's like I am going to, I'm sorry, the height of this is 1 over t, because this 1 over t times this is 1. So when I expand it out again, what happens is this, the 2 over pi's turn back into the sampling frequencies. And what used to be the cutoff becomes W cutoff over T, which is the same thing as W cutoff times omega s over 2 pi. Okay. Again, the height of this thing continues to be 1 over t. This is now continuous time Fourier transform of basically this is like yd spread out by this. And then when I do my reconstruction filter to notch out the middle copy. So that reconstruction filter you can think of as either operating in discrete time or on continuous time. So if I think about that in think about this for a second. So in continuous time, that filter is going to have basically a bandwidth of this, right, pi over t. And then the product of those two things in the frequency domain gives me just the middle copy, which is going to have height 1, and it's going to have cutoff omega c over t, as long as I don't have any aliasing or anything like that. And this is the continuous time Fourier transform of my reconstructed signal, right? And so now if I compare the beginning to the end, right? So if I compare the beginning to the end, I started with this, and I ended up with this, right? And so you can see that what I did was I effectively filtered this continuous time signal as if I was applying a continuous time low-pass filter that had a band edge of omega c over t. And so that's just kind of like a recapitulation of the whole thing I talked about. So the idea is that, you know, if I had a discrete time cutoff of omega c, then I have a continuous time cutoff of omega c over t. And kind of what this suggests, which is actually kind of interesting, is that, you know, I can accomplish many different continuous time filters simply by designing one really good digital filter with a certain cutoff and then running it through sampling systems with different sampling rates, right? So if I want to vary the continuous time cutoff, all I need to do is change the sampling rate of the input and then run it through this single great digital filter that I've designed, right? So that's kind of an interesting approach, is that, you know, I design a great fixed digital filter, and then I modify the effective continuous time filter by changing the sampling rate. And so that's kind of a neat trick, right? So instead of kind of thinking about a digital signal as something that is kind of given to you by fiat, that this is just the sampling rate that you have, this kind of tells me that I can I'm allowed to choose a sampling rate, right? I'm the sampler guy, so I can do whatever I want to make the effective system do what I want to do, right? So I'm allowed to choose a sampling rate to make the continuous time effective signal do the right thing. And so that's kind of a clever idea. And so there are a bunch of kind of caveats in this process. You know, one is basically, you know, you need to make sure that the discrete time system is LTI. And the other one is that the sampler must be above the Nyquist rate of the input. Right? Because if the input is not sampled fast enough, then everything kind of goes to hell, right? Because you can have all these overlaps, and the effective thing that you get isn't actually what you thought you were going to get because of the aliasing, right? So that's really kind of important. Otherwise, you know, you might not be able to actually get this to work. Okay. Okay. So my final note on this before I go on is that kind of how are the impulse responses related, right? So I kind of talked about how things work in the frequency domain. Basically, let me just make one quick mention of how are the impulse responses related. So the idea is that if I have a time domain desired impulse response that looks like, this. Again, since we're in continuous time, this is a, continuous function, right? Then the digital filter that kind of corresponds, assuming again that everything is valid with Nyquist, so the digital filter that corresponds to this desired response is given by this. Let me just write this slightly differently. I was too aggressive with that subscript. What that means is that to get my digital filter samples that correspond to this thing, what I should do is sample it every t units and multiply those samples by capital T. Right? So this kind of tells me if I know what is my ideal continuous time impulse response, I can immediately kind of pick off what are the corresponding values, right? So I don't have to go through this whole thing in the frequency domain to figure out what to do in the time domain. And this property of this holding true is what's called impulse invariance. And we're going to talk about that a little bit more when we talk about filter design. And so kind of where we're going, so this week we're going to spend on just cleaning up a couple issues related to sampling, but the next few lectures are going to be devoted to, okay, so now that I know how I can take a digital filter and make it work for me in continuous time if I wanted to, then we're going to talk about, okay, well, how would I design a good digital filter, right? That's going to be kind of where we're going next week. Okay, so let me just pause and ask questions about this, right? I know this is a lot to, there was a lot of math, a lot of pictures, but fundamentally, the main thing that I want you to understand is kind of this process of the graphs, right? So if you understand this process, you'll be good, right? So you should be able to kind of immediately say, okay, I know that things in the continuous time world, the copies occur at multiples of the sampling frequency. In the discrete time world, they occur at multiples of 2 pi. And then if I'm doing a filter, I need to do this conversion between the copies at omega s and the copies at 2 pi. And that results in this kind of scaling of the effective frequency response to the filter. And so you might look for questions on the next exam along the lines of, I want to design a filter that in the continuous time domain has a cutoff of 10,000 hertz. I sample that signal at 40,000 hertz. What should the cutoff in the digital domain be? Pi over what, right? So that kind of thing is just a question of understanding how to convert back and forth between cutoffs and sampling rates and 2 pi's and omega s's. Okay. So questions or comments about that? Okay. So now what I want to talk about is something a little bit easier, which is changing the sampling rate. Okay. And, let's see, I know my pen is dying, but I don't think I have a better pen. I guess maybe that's nominally better. Okay. So changing the sampling rate is something that happens a lot in practice. So, a common problem is better or worse? It's about the same. I guess the old one was thicker, even though it's dying. So the common problem is that we have, some discrete time signal that came from sampling a continuous time signal every n units, and what we want, for some other reason, is a discrete time signal that came from sampling this guy at some different rate, where these two things are not equal to each other. Okay. So how would we go from x of n to x prime of n? right? So assuming everything is sampled above the Nyquist rate, in theory, there's the long way around, right? What I could do is I could take my samples, reconstruct the original continuous time signal, and resample it to get back to the digital signal, right? And, that is true. I could do that, but that seems needless, right? Because really what I want is a fully digital operation that goes from the original samples to the new samples, right? And, I may not be able to create analog signals inside my processor anyway, right? So, long way, or a theoretical way, is, assuming fast enough sampling is to reconstruct the continuous time signal and resample. Right? We really don't want to do that if we can help it. So is there an equivalent discrete time approach? Okay, so what I'm going to talk about are basically two different ways of doing things. So these are called kind of upsampling and downsampling, okay? And so let's talk about some easy cases first, okay? So downsampling at an integer rate. So what does that mean? That means that basically my, downsampled signal is my original digital signal taken every m units, which is the same thing as if I had sampled the continuous time signal every mt units, right? So sometimes I represent this like this block that says downsample by a factor of m. So here the original sampling rate was t, and here the sampling rate is basically mt. And sometimes you hear this called a compressor. And so how would I do this? Well, this is just really easy. This is like saying I take my original signal and I take every capital M sample. Again, here m is going to be an integer, right? So m is an integer. So what do I do? It's like saying, okay, here's my original discrete time signal, and say n was equal to 3, that would be like saying I take this sample, skip these two, take this sample, skip these two, and so on. Right? So it's just like taking every third sample. So I guess I have to face the reality that my pen is dying. So that's like saying I would get this, 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 and so on. Right? So this is my x of n. This would be what I would get if I downsampled by 3, and this would be my new x down of n. Okay? So it's definitely true that if my original signal was sampled fast enough, really fast, so if this original signal was sampled at least capital M times the Nyquist rate, then I should still be able to reconstruct the original signal from these samples, right? However, it's possible that in the process of downsampling, I remove kind of critical information that I would need to reconstruct the signal, right? And so what I want to talk about is what's happening in the frequency domain when I downsample, okay? So let's talk about the frequency domain relationship between this signal and this signal, okay? So again, this is something that's a little bit easier to think about in pictures. than it is to do it in symbols, but I'm going to do the symbols first and then the pictures. Okay. So the frequency domain relationship so what's happening there? Well, the DTFT of my original signal is basically, I've got all these copies. The height of the copies is 1 over t, and I have the copies are centered at the multiples like this, right? So here, this is the Fourier transform of the continuous time signal. Okay. And then what I want is a Fourier transform that looks like this, but sampled at a different rate. So this is kind of what I want. So this is t prime. But I know that my t prime is defined as some multiple of t. And now what I'm going to do is I'm going to split this sum here into m pieces, right? So kind of similar to the way that we use this trick in the DFT algorithms for turning this, turning this k into, a two-dimensional signal. So we're going to do the same thing here. So I'm going to say, I'm going to take the m out here. I'm going to have one sum that goes over m. I'm going to take this guy, and now this sum is going to go over kind of multiples of m. This part stays the same. And all I'm doing is I'm rewriting k to be I plus km over mt. Right? So all I've done basically is I've kind of turned this sum into this, where it's like saying, the inner sum adds, when k equals 0, it's like I'm summing up from 0 to m minus 1. When k equals 1, I'm summing up from m to 2m minus 1, and so on. So I'm just kind of taking these pieces apart. And now I can write this in a slightly different way. So I've got this 1 over t, this sum. I'm going to move this guy over here. And, this thing here, right, looks exactly like this thing over here, except I'm plugging in a shifted value of the input, right? So what I have here is I have basically m copies of the input shifted by multiples of 2 pi over m. Okay, so I know this is a little bit confusing mathematically. This is saying that the downsampled DTFT is related to the original sampled DTFT by a bunch of scaled and shifted copies, right? And this is really the same thing that happens when I sample a signal to begin with, right? And if I think about things in the frequency domain, it actually should just make sense, right? So let me just show what I mean. So again, let's start with some original continuous time signal. We're going to sample it with sampling rate capital T, and then we're going to sample it with sampling rate capital MT. Okay. So here's my original Fourier transform. This is my CTFT. I have omega. This is my original continuous time signal. And let's suppose that it's got some band limit omega b. Okay. So now I am going to sample that signal at a rate of t. So this is basically x of omega, the DTFT, and here the rate is t, right? So that means that I'm going to get a whole bunch of scaled and shifted copies. And since this is a DTFT, these guys have to be periodic with period 2 pi. The band limit becomes basically a scaled version of what it used to be. And the height of these copies is 1 over 2. Okay. And so what is the, what is, oops, not this thing. What is this thing telling us? Right, this is telling me that to get to the new downsampled signal, fundamentally what I'm doing is I'm making copies and I'm stretching the frequency axis out by a factor of m, right? So what happens is I am basically still getting 2 pi periodic copies. This is my downsampled DTFT. Now this is going to be rate capital MT. Well, what happens is, I should have drawn this a little bit differently, but what happens is that my copies will shrink down and spread out. So they're going to have a different height, and they're going to have a different band limit. And the bad thing is that, when I do this, it's highly possible that I can get aliasing, right? And actually, I don't even need to have that formula to draw this picture, right? So I mean, here, suppose I didn't tell you anything about the previous slide. I just said, okay, what would I get if I sampled this at rate t? I get this. What would I get if I sampled it at rate mt? I get that, right? And certainly, if I'm sampling less often, my Fourier transforms have a much higher probability of aliasing, right? And so the only way that I can downsample the signal, the original discrete-time signal, without getting aliasing is if I happen to have sampled that signal very fast to begin with, right? Because the effect of downsampling is to spread out these copies even more in the frequency domain. So aliasing can definitely occur. And, we would have needed to sample the original signal at least m times the Nyquist rate, right? Because if I don't have room for those m copies to spread out, I'm certainly going to introduce aliasing in my downsampled signals, okay? So for example, let's do a little thought experiment. So let's suppose with some concrete numbers that this was the Fourier transform of my original signal. So let's suppose I have like a triangle like this, and that the triangle width is pi over 2. Okay. So what happens if I downsample this by a factor of 3? Well, what that says is that these triangles are going to shrink down by a factor of 3 and spread out by a factor of 3, right? So it used to be pi over 2 is going to become 3 pi over 2. And what used to be 1 on the y-axis becomes a third. And so my my new signal, DTFT, is going to look something like this. And this guy here is definitely going to be overlapping when I do the copies, right? So the new height of this is going to be 1 over 3, and there's going to be serious aliasing happening over here. Okay. And so one solution, kind of, it's not great, but it's the best that we can do, is to say, okay, well, I can predict what the maximum bandwidth of the original signal would need to be to prevent the copies from overlapping, right? And so what I could have done is said, okay, before I do the downsampling, I am going to pre-filter the signal to prevent the aliasing from occurring. And so what I could have done is to say, pre-filter the signal in this way. So to prevent aliasing, or I'm just going to say solution in quotes, because it doesn't really solve the problem, it just kind of mitigates the problem. I can pre-filter the original discrete-time signal with a low-pass filter with bandwidth 2 pi over m. Right? Why is that? Well, what would happen in this case? So that would be like saying, okay, 2 pi over 3 So again, let me think about this for a second. Well, so I guess when I say bandwidth, I would be like saying like this. So what I mean is a signal that looks like this. What would happen if I did that here? So here, that's like saying, where is pi over 3 going to be? So this is like going to be like here. What I could do is I could apply a low-pass filter like this, cut out this junk here initially. So if I pre-filter the signal, what I'm going to get is something that looks like this. I'm going to have this guy. Like this, 5 pi over 3. This is going to be negative 5 pi over 3. And then when I downsample this signal by a factor of 3, I'm going to get these copies spreading out. But the way I did this, the copies are not going to overlap, right? So the downsampled version is going to spread these guys out, but there won't be any actual aliasing. What will happen is that what used to be pi over 3 kind of becomes pi. And then this copy over here kind of similarly will spread out, but I have cut away the part that might possibly alias before I did the computation, right? So this kind of the idea is that, you know, no aliasing, but the downsampled signal doesn't represent the original. Right? And actually, if you remember when I was showing you the music example, right? We were doing the RES, sound sample, right? That's exactly what I was kind of talking about, was that the original sound sample was sampled at 44 kilohertz, and I was changing the sampling rate. And even though I knew that by downsampling it, even by a factor of 2, certainly, that would be, so certainly there are high frequencies that the human ear could hear that are going to get aliased into, the audible band with this kind of thing going on. But as long as there's not a lot of high frequency content, I may be able to get away with this for a while. As you noticed, right, if I really cranked up the downsampling factor, ultimately I got something that was too garbled, right, because all the stuff overlapped into the low frequency band. I could have tried to pre-filter that signal with a low-pass filter. Then what I would get basically would be a reconstructed low-pass version of the original sound, right? So in some cases you may be able to get away with it, and in other cases you may not. Okay, so let me pause and ask about downsampling. Any questions about downsampling? Yes?
Let's say that high frequency information is important to us.
Mm-hmm.
We know we have to downsample. Could you kind of construct an effective Nyquist frequency which will allow you to downsample but still keep that?
I mean, you
carry
can't.
It to that scale
I mean, you can't really have, so if you know the high frequency information is important, but you also know that your sampling rate is somehow insufficient, it's below the Nyquist rate to capture it, then you're kind of stuck, right? I mean, you're going to lose that information either via aliasing or via low-pass filtering with the pre-filter, right? I mean, you can't have it both ways, right? If you know that you need that stuff, then you need to be sampling fast enough to get it, is what it comes down to.
So the limiting factor is most of the time is sampling.
Yes, the limiting factor is the sampling rate, right? So you have to sample fast enough. Yeah.
If you're looking for, say, a single frequency, and you were to undersample it so that it actually aliased down, into the frequency range, would you theoretically sample a signal that's higher than your sampling frequency?
Yeah, so that's an interesting question. So I thought about assigning a problem like this on homework, but I didn't. So if I understand your question correctly, you could say something like, suppose that I had a bandpass signal like this, right? And this was the spectrum. Now, Nyquist would tell me that I would have to sample at twice this rate to avoid aliasing, right? But you could imagine that if I sampled kind of shrewdly, and let me think about if I could put some numbers on this to make it work. I mean, you could imagine that what I could do is, supposing that I sampled exactly at this rate, for example, right, which is in theory too low, my copies would look something like, this, right? Here's one copy, here's the original, here's the other copy, right? So there's a way for kind of band limited signals where I can sample at a rate that is lower, possibly much lower than the Nyquist rate, but avoid copies in the frequency domain. And if I knew that that was the characteristic of the original signal, then I could certainly design things that would sample at a lower rate, but be able to reconstruct the original signal ideally, right? So that's a kind of a fun little problem to figure out, is that if you knew, for example, that the thing I cared about was in some very narrow frequency band, then certainly the intuition is that the Nyquist rate that you should be able to, that the sampling rate that you should be able to achieve should be related to the kind of non-zero bandwidth of the signal, not this whole distance, but only the part that's occupied, right? And that intuition is correct, right? So you can get away with very low sampling rates as long as you kind of know this a priori. You have to know that band. Like you can't just get away with knowing that the signal is like 100 hertz wide somewhere in the frequency spectrum. You have to know exactly where that is to know where the copies are going to land, right? But it may be that you know exactly what your spectrum of interest is, and then that would work, right? Yeah. So there are a bunch of little professorly homework problems about, if you have a signal that looks like this, question number one is, what's the Nyquist rate? Question number two is, can you sample slower than the Nyquist rate and get a filter that you could use to do pre-reconstruction? And the answer is yes, right? And you have to do that by drawing out where these copies can occur and making sure that no copy hits any other copy, right? Yes, so it can be done. Yep. Let me just also mention, while I was talking about sampling, so I assigned a problem for the grad students, the lucky few. So when I was in grad school, my professor assigned me this problem about the intuition is also true that I shouldn't have to take equally spaced samples, right? I shouldn't be limited to that. The idea should be that as long as I'm taking, on the average, enough samples per interval, and that number of samples is above what the Nyquist rate tells me, I should be able to reconstruct the signal even if those samples are not uniformly spaced. And in fact, that's true, but it's a real pain to actually make it work, right? So for example, the homework problem I gave is saying that ideally, maybe the samples should be spaced out this far, but the theory is that as long as I have a couple of samples every period, I should be good enough, right? And so the question of how do I reconstruct the signal from these non-uniformly spaced samples is a little bit tricky, right? And so good luck on you graduate students for doing this problem. And also, but you can see from the solutions that you've got kind of a similar idea of like, this set of impulse trains gives me kind of one set of copies, this gives me another set of copies. And you think about how do I have to make sure these copies cancel each other out the right way in the frequency domain. And in fact, there are all sorts of variations where you say, okay, I don't even necessarily have to do regular sampling in the frequency domain. Instead, I can do sampling, kind of almost randomly, as long as I have the expected value of the number of samples per period is the right number, right? So there are lots of interesting extensions to the sampling theorem. In fact, one of my friends was just telling me about an interesting extension where it was something like you've got a sensor network, and the sensor network waits to see how long it takes for the sum of its samples to add up to a certain value, and then as soon as the sum hits that point, it sends out a message to the network that says, I accumulated that point after, time t, right? And somehow, just by knowing the rates at which these sensors are hitting capacity, you can reconstruct the original signal, some sort of slick thing, right? So if you like this kind of, mathematical manipulation in both time and frequency, there are lots of interesting extensions to do. Okay. So, more questions. That was a good discussion. I'm glad I brought that up. Okay. So, let me think about this for just a second. About whether I want to get into this. Okay. Let me just say a few words about upsampling, and I may be able to, I may say more about it next time. So, upsampling is the process by which we increase the sampling rate, right? We get more samples than we had before, okay? And so that's like saying that, we have x of n is some set of samples like this, and we want x upsampled of n to be equal to the continuous time signal sampled at some faster rate. Okay. And just like there is a little block that looks like a little down arrow, there's also a little block that looks like an up arrow. And just like the other guy was called a compressor, this guy we can call an expander. And so what does that do? Well, this guy is going to insert zeros between my original samples. So, for example, if I have, a set of original samples, and I put it through an upsampler 3, then what happens is I get the original samples, and then between every pair of samples I get a couple of zeros. Okay. So this is not quite what I want, right? What I want is kind of like something where instead of getting just zeros, I get kind of like connecting the dots. I want to kind of hallucinate what should have happened between these samples, okay? But the nice thing is that to get from here to here is actually a very easy process, as we can see in a second in the frequency domain. And the reason for that is that, assuming that I've already sampled the signal fast enough, if I've sampled the signal fast enough and it's above the Nyquist rate, then in theory, I know that I could always bump up to the original continuous time signal and sample it however fast I wanted. So all the information to make more samples is implicit in my original set by assumption, right? If I sampled above the Nyquist rate, then I've got all the samples I needed from the get-go. I should be able to generate as dense of a sampling as I want from now on, right? And so again, let's think about what's happening in the frequency domain. So maybe I should say, first of all, let me just be a little bit clearer. So what is the expander doing? So the expander is saying, well, when my n is a multiple of L, I basically am taking that corresponding sample, and it's 0 otherwise. Okay. And so how to create the upsampled version of n from the expanded version of n, right? So the distinction is that the expanded version just has a bunch of zeros in the gaps. The upsampled version actually has the correct values inside the gaps. Well, it turns out we just pass it through a low-pass filter that looks like this. And I'm going to call this my kind of interpolation filter. Right, because interpolation is really a fancy word for connecting the dots, right? And so it turns out that by simply filtering my expanded signal with this, I get the right answer. And so let's understand why that is true, okay? Okay, so in the Fourier world, right, I have that my expanded Fourier transform is going to be just this guy here, my expanded signal, e to the minus j omega n, right? And what does my expanded signal actually give me? Well, this is like saying that I have every L units, I get my original signal value. And then the value that I get is e to the minus j omega n L. Right? So I'm only basically hitting my original signal at these places. And this is the same thing as the original Fourier transform, just, actually, let me be a little bit careful about this. Right. Let me just write a note to myself here. So this expanded signal is equal to, no, it's like this, right? Right, that's like saying that the NL value, this is the only thing that's non-zero, and that turns out to agree with x of n, right? So that means that I'm basically getting the Fourier transform of my original signal just compressed in the frequency domain by L, right? Because L is some integer. And so what does that look like? Well, that looks like, if this is my original continuous time signal, again, going back to the original sampling, so if my original continuous time signal looked like this, now I sample it at some original rate. When I sample it, I get the spread out and aliased copies. So those copies occur at multiples of 2 pi. Height becomes 1 over t. The bandwidth becomes t over omega b. And so what is the Fourier transform of the expanded guy? That's telling me take this thing and squish the frequency axis by a factor of L, right? So I can see that by inserting the zeros, there's no way that I can get any sort of like aliasing, because all I'm doing is I'm taking this whole thing and I'm squeezing it down, right? So what used to be 2 pi becomes 2 pi over L. So now what I get is kind of like this squishy copy where I've got, you know, so say I do it by a factor of 3. So now all I'm doing is I've squeezed this together, and this guy becomes t omega b over L, and the first copy occurs at 2 pi over 3, and the next copy occurs at minus 2 pi over 3, and so on, right? And so here, now it's kind of easy to see that all I need to do to notch out or to get the original signal back is to notch out the middle copy, right? So the height of these guys is going to be 1 over t. And so if I am to notch this guy out, I need a filter that looks like this. So my interpolation filter is basically something that notches out only the copies that are centered at multiples of 2 pi. Because again, remember this is a discrete-time filter. I'm going to make the height of this filter L, and I'm going to make the bandwidth of this filter pi over L. And now when I multiply this by that, what I get is just skinny copies that are centered at multiples of 2 pi. The height of these copies is going to be the L from here and the 1 over t from there. And then these guys are going to be omega b t over L wide. And this is exactly what I would have gotten. So this is exactly what we'd get by sampling at t over L in the first place. Right? So that's pretty slick. This is just saying that I can take my original samples, spread them out, put zeros in there, run that through a low-pass filter, and that low-pass filter will correctly and magically fill in the right samples in between, right? So that's pretty cool. So that means that I don't actually have to do anything in continuous time. I just have to do the zero insertion process and the low-pass filtering in discrete time, and everything works out. And so this whole system of inserting the zeros and then applying the low-pass filter is sometimes called an interpolator, right? So kind of what I need to do is build a system that is combined of, you know, a expander block and a low-pass filter block. Right? This whole thing is all I need to upsample the signal by an integer rate. And again, if you think about what's happening in the time domain, right? This thing is a pulse, so that means that if I have a kind of a interpolation function in the time domain, that's some sort of a sinc function, right? And you can write out what that sinc function is. And so fundamentally what I'm doing is I'm taking the sample like this, and I'm adding up, you know, a bunch of, I'm kind of thinking about these numbers as weights on these sinc functions. And again, all these sinc functions will magically add up to the right thing in the middle samples, right? Because really this is nothing more than the kind of interpolation that we would normally do for reconstructing the signal, right? And kind of the intuition is that, you know, at some point, if the signal is like super oversampled to begin with, right? Like if it's sampled much faster than it needs to be, then certainly in the real world it may be possible I can get away without doing this whole proper thing. I could just connect the dots between the samples and be pretty sure that nothing bad was going to happen between them. But you know, this is the right thing to do in practice. And so I think that I'm going to stop there. Kind of a preview for next time is going to be that, you know, this tells me, so what I've answered today is, okay, if I want to increase the sampling rate by a factor of 3 or decrease it by a factor of 4, how do I do that? But what if I wanted to change the sampling rate to say, okay, instead of getting 100 samples inside this interval, I want 103 samples inside that interval, right? So that means I'm changing the sampling rate by a non-integer factor. And the question is there a more efficient way of doing it than to basically upsample by a factor of 103 and downsample by a factor of 100. Because in doing that, I'm generating lots and lots of extra samples that I'm throwing away, right? And so the topic of the next lecture is basically going to be kind of what I would call multi-rate signal processing. And the theme of that is going to be how do we do signal processing operations in efficient ways where we're not doing a big filter and then throwing pieces away. We want to make sure that our computation is as efficient as possible. And so you can do that by decomposing some high-rate signal into a bunch of lower-rate signals. And that's what we're going to talk about next time. Okay, so any questions about upsampling? Yes? Can you reduce the error by using? Well, I mean, in some sense, you can never reduce the error beyond the sync interpolation, because the sync interpolation is the ideal correct thing, right? If I do this, I get exactly the right samples. You can analyze the error that you get by making a linear interpolation assumption, right? So you can say, okay, you know, it turns out, for example, that okay, without going into too much detail, so let's just say, because I have it in my notes that I can write down, it turns out that the effective filter for linear interpolation looks like this. Kind of the ratio of two sync functions. And you can kind of plot out, okay, so this is the ideal reconstruction filter. So this is my ideal HI of omega. And if you plot out what is the kind of non-ideal linear interpolation look like, it kind of looks like, you know, something like this. Apologies for crappy drawings. Right? And so you can kind of say that, you know, the bandwidth of this wavy thing depends on L, basically. And so fundamentally, there are ranges in which, you know, the ideal reconstruction thing and the sync function thing maybe look close enough that you can get away with it, right? And you can analyze what is the error between, I guess you have to have you may have to have a probabilistic model for your signal, but you could say, you know, what's the expected value of the error for linear interpolation if I'm oversampled by a rate of blah, right? So yeah, so you can do those kinds of things, but I mean, you can never do better than the sync function because the sync function gives you back the exact samples, right? But yes, people have analyzed that kind of thing. Okay, other questions or comments? So let me just make a quick note while I'm shutting down about the homework. So I posted